Okay. So if this happens, then x comma x is x square, which is always greater than 0. Okay. So x is related to itself. Next is you have to show R is symmetric. Okay. R is symmetric. Symmetric. So let x comma y belongs to R. Okay. Then what happens? X into y is strictly greater than 0. Okay. So from here, so if the product of two numbers is greater than 0, then both the numbers should be positive or both should be negative. No? So this implies x greater than 0, y greater than 0, or okay. This is one case. Another case is x is less than 0, y is also less than 0. So if x and y are both positive, then y into x is also. Oh, we can write it from here. Xy is same as y. We don't need this also. From here itself, I can write yx is greater than, because xy is always same as yx. Okay. Commutative. Multiplication of real numbers is commutative. Okay. So yx is greater than 0. So from here, y comma x is an element inside the relation. Okay. X comma y, yx belongs to R. Okay. Next is R is transitive. R is transitive. How will you show? Let xy belongs to R and yz belongs to R. Okay. So here I will make something. So this means x into y is positive and y into z is positive. Okay. Right. X into y is positive, y into z is also positive. Okay. But so if x greater than 0, y greater than 0, okay, then z also should be greater than 0. Okay. Yes, sorry. If y greater than 0, z greater than 0, then yz greater than 0 will imply that. Okay. Then yz greater than 0 implies z should be greater than 0. Okay. Right. Xy greater than 0 means both xy should be positive or both xy should be negative. Okay. Just let me add another line here. Multiply. Oh, you can do it that way also. If you multiply, this is positive, multiply this to x, y squared z is positive. Out of this, y squared is positive, so we can divide by y squared. Okay, yeah, that's a better way of doing this. This into this is greater than. So therefore, xy multiplied with yz, this is also greater than 0. So from here we have x into y square z is greater than 0. Okay, but since xy is greater than 0, so that means y is positive. Y is non-zero. Okay, so y square is always greater than 0. So xz greater than 0. Okay, since y square is positive. Okay, so we can divide inequality by a positive point. Okay, y square is always positive. Okay. So from here xz is greater than 0. So x comma z belongs to R. X comma z belongs to R. Okay. So R is transitive. Okay. So it's reflexive, symmetric as well as transitive. So it's an equivalence relation. Okay, so I'll give you some homeworks, you try. Okay, try solving. try this homework. We try that define relation. Similarity. Yes, this symbol is on R squared as x1 y1 related to x2 y2. You can only x1 square plus y1 square is equal to x2 square plus y2 square. X and x, this two are related if x1 square plus y1 square is equal to x2 square plus y2 square. Okay. So here we have just changed the notation. Okay, notation change for C because here the set that we are considering is itself R square. Okay. So if I write it in terms of order pair, it will be something like this. This x2 y2 belongs to this. Okay, so it will be clumsy. Basic brackets will do. So this is another way of writing. Okay. So in fact, this AB belongs to R. Another way of writing this is A related to B. Okay. So this is the system. So means the set that is given is itself a set of ordered pairs. Okay. So two ordered pairs will be related if this x1 square plus y1 square is same as x2 square plus y2 square. Okay. So on R square, what does it represent? What does it represent? This expression. What does it represent in the Cartesian plane? Huh? What does it represent? If x1 y1 is a point, say x1 y1 is a point here. What does this represent? Huh? Circle, na?
Sir, go hypotenuse. Hypotenuse.
Hypotenuse. This expression represents what? Square of the distance of this point from the origin. Okay. Distance of this point from origin is what? Root over of x1 square plus y1 square. So this actually represents the square of the distance from the origin. Okay. So two points are related if they are at the same distance from origin. Okay. This is the meaning here. This relation, under this relation, 2 points are related even only if they are at the same distances from the origin. Okay. So all points on the circle are related. Okay. All points on this circle are related. Okay. So that way. This represents equation of a circle when I write it as this x square plus y square equal to some constant. Okay. Right. And as a particular expression for a particular point, it represents the distance of that point from the origin. Okay. So all points on this circle, on a fixed circle, are related to itself. Okay. So that is what. So you try to show that this is actually a equivalence relation. So reflexive is very simple. X1 square plus y1 square is always same as x1 square plus y1 square. Writing the same thing two different times. Symmetric is also simple. No? Just change the LHS, RHS change for it out. It's all the same. Okay. It's very simple. Like just equality to ultimately it's similar to equality. So you can do that. No? Okay, another thing you can try to think about, let R and S be equivalence relations on let R and S be equivalent relations on say X, on a set capital X. Okay. On a set on a set on X. Okay. Is R union S an equivalence relation? Equivalence relation. Okay. Is R intersection S an equivalence relation? Equivalence relation. Okay. Try to think about this. Union of two relations is also a relation. Okay. Intersection of two relations is also a relation. Okay. So if I have two equivalence relations on a set X, whether their union is also equivalence relation, whether their intersection is also equivalence relation or not. Okay, that's what you have to think. Next, we have a concept called equivalence class. Equivalence class. Equivalence class. Let R be an equivalence relation. Equivalence relation on say some set A. Okay. Then and small a belongs to capital A. Be any element. Be an element. Then equivalence class of A. Then equivalence class. The equivalence class of A with respect to R. Okay. With respect to, or should I say, with respect to R, which we have defined. Equivalence class, then the equivalence class of A for the relation R. Okay, for the relation or with respect to also this, okay. For the relation R is defined as, denoted and defined as, okay, denoted and defined as, again, we have denoted by this square bracket, okay, third bracket. Equivalence class of A, it is the set of all those X inside A such that X is related to A. Okay. X comma A belongs to R. Okay. So it is the set of all those elements of A which are related to small a. Okay. Right. Equivalence class of A, when A and B are related. Okay. Those elements are there inside this equivalence class. Okay. So equivalence class of A is a subset of which set? This is a subset of what? This equivalence class of A is a subset of which set? R subset. Whose subset is this? Simple, from the definition itself you can see. It is a subset of what? It is a subset of A only. Okay. Equivalence class of A is the set of all those elements of A which satisfy something. What do they satisfy? They satisfy that they are related to small a. Okay. So it is a subset of A only. No problem. Okay. So given an equivalence relation, we can define an equivalence class. It is the class of, it is the set of all elements of capital A which are related to this small a. Okay. So let us see. For example, suppose I take A equal to say 1, 5, 8, okay, and R is an equivalence relation 1, 1, 5, 5, 8, 8, say 1, 5. So if I include 1, 5, I have to include 5, 1 also. Right, so this is an equivalence relation. R is an equivalence relation. Equivalence relation on A. Okay. So what is equivalence class of A? Equivalence class of A, it is the set of all those elements in A such that x comma 1 belongs to R. Okay, or this is an equivalence relation, or 1 1 x belongs to R. Same thing. Okay. Right? Those elements which are related to A. So it is the set of all elements. So here you may write it, set of all elements of A which are related to small a. Okay. So what is the equivalence class of A here? Huh? No. Equivalence class will not contain these ordered pairs. Ordered pairs are elements of the relation. You have to just identify which elements they are related. One is related to 1. So 1 is there. Then 1 is related to 5. 5 is related to 1. So 5 is there. So only 1 and 5. Okay. So this is the equivalence class of this one. Okay. Similarly, what is the equivalence class of 5? Equivalence class of 5. So 5 is related to which elements? 5 is related to 5. 5 is also related to 1. Okay. So it's also 1 5. Okay. What is equivalence class of 8 here? 8 is only related to itself. Okay. It is not related to any other element. So equivalence class of 8 is 8. Okay. Clear. Similarly, we have seen another one. So let us try that also. So for the relation, another example for the relation R on Z defined by what? A comma B belongs to R. You can only 5 divides A minus B. Okay. What is equivalence class of 0? Equivalence class of 0. Equivalence class of 0 में देखिए था all those elements which are related to 0. Okay. तो 0 लोग क्या कारा related है तो 5 is related to 0. So 0 minus 5 is minus 5. Minus 5 is divisible by 0. Okay. 5 is related. Any other element? Minus 5, 10, everything is related. Minus 10, okay. 15, minus 15, okay. Everything else. Okay. So this is actually the set of multiples of 5. 5n, so that n belongs to integers. Okay. Because if A is related to 0, A comma 0 belongs to R implies what? 5 divides A minus 0. Okay. This means 5 divides A. So A is of the form 5n where n belongs to that. Okay. This is how we prove. How to prove this? Equivalence class of 0 is this. So let A belongs to equivalence class of 0. Okay, like this. Prove it. Let A belongs to equivalence class of 0. What is the meaning? This means that A is related to 0. Okay. A comma 0 belongs to R. Or equivalently, you can write 0 A belongs to R because R is an equivalence relation. So it is already symmetric. Okay. So if A is inside equivalence class of 0, then A comma 0 is in R. What does that mean as per the definition? As per the definition, it means that 5 divides A minus 0. That means 5 divides A. So if A is divisible by 5, then A can be written as 5n such that n belongs to natural integers. Okay. So any element inside equivalence class of 0 is of the form 5 into something. Okay. 5 into some integer. So it is the set of all 5n such that n belongs to integers. Okay. Right. Any arbitrary element of this is of this form. Okay. Conversely, any element of this form is also inside equivalence class of 0. So this is there. What is equivalence class of 1 here? Equivalence class of 1 under this relation. What is equivalence class of 1? 6. 6 will be there then. 11 is there then. What else? 16 will be there. Minus Minus 6 is not there. Minus 4 is there. Minus 4 will be there. 1 minus minus 4 is 5. Is there. Minus 9 is there. Okay. Then minus 14 is there. Okay. 1 is there. 1 is inside. Okay. So how can I write this?
5n minus 5n plus 1.
We can write this one as 5n plus 1 so that n belongs to integers. Okay, it is the collection of all this. How will you prove? The proof is exactly similar. Let A belongs to equivalence class of 1. So this implies that A is related to 1. A comma 1 belongs to R. Okay. This means that 5 divides A minus 1. Okay. So 5 divides A minus 1 means A minus 1 can be written as 5 into n where n belongs to integers. Okay. So A can be written as what? A is written as 5n plus 1 where n belongs to integers. Okay. So any element inside this is of this form. Okay. Any element inside this is of this form system. Okay. So it is the set of all 5n plus 1 such that n belongs to integers. What will be equivalence class of 2? It will be 5n plus 2. Okay. It is the collection of all elements which are of the form 5n plus 2 such that n belongs to integers. Okay. Similarly, what is equivalence class of 3 under this relation? It is the set of all those elements which are of the form 5n plus 3 where n belongs to integers. Okay. And equivalence class of 4 will be the set of all elements of the form 5n plus 4 such that n belongs to integers. Okay. What is equivalence class of 5? That is the set of all elements of the form 5n plus 5 such that n belongs to integers. How many equivalence classes will be there here for this relation? Huh? Infinite or what? Huh? Infinite or finite? No, actually it's finite. Okay. See, when you come to equivalence class of 5, you can write this one as 5n plus 5. This can be written as what? 5 into n plus 1. Okay, so this actually is that one, equivalence class of 0. This is same as equivalence class of 0. Because this is a multiple of 5. 5n plus 5 into n plus 1. This is a multiple of 5. Okay. So this equivalence class and this equivalence class are actually the same thing. Okay. Right? These two are the same thing. Okay. So we will show how these are same. Similarly, if you come to equivalence class of 6, this will be same as equivalence class of 1. Okay. Equivalence class of 7 will be same as equivalence class of 2. Okay. So this under this relation there are only 5 equivalence classes. Okay. Under this relation, so under this relation means congruence modulo 5. Under this relation, congruence modulo 5. Okay. There are exactly 5 distinct equivalence classes. Okay. Distinct equivalence classes. Okay, what are those? Equivalence class of 0, equivalence class of 1, equivalence class of 2, equivalence class of 3, equivalence class of 4. These are only distinct. Equivalence class of 5 will be same as this, 0. Okay, equivalence class of 6 will be same as this. Okay. So what is happening is actually we are finding out remainders. Okay. See, equivalence class of 6. If any element is inside equivalence class of 6, what does it mean? A comma 6 is inside R. That means 5 divides A minus 6. Okay. That means A minus 6 can be written as 5 into some integer. Okay. So from here I can write A as 5n plus 6. Okay, but this 6 again I can write as what? 5 plus 1. Okay, so this is ultimately 5 into n plus 1 plus 1. Okay, so it is of the form So it is of the form 5 into something plus 1. Okay. So it is the set of all any element inside that can be written as 5 into some integer plus 1. Okay. So it is actually this type of element, they belong to equivalence class of 1. Okay. This type of elements are there in equivalence class of 1. Okay. So that is the thing. So they are actually the same. So we will try to show how these are. Okay, so there are some properties of these equivalence classes. So if I have this relation AB belongs to R, if and only if say 100 divides A minus B, then what are the equivalence classes? Then equivalence classes are what? 100 divides A minus B. What are the equivalence classes? Equivalence class of 0, equivalence class of 1, 2, up to what?
99.
You go up to 99. When you go to equivalence class of 0, there will be a repetition. It will be same as equivalence class of 0. But when you go to equivalence class of 100, there will be a repetition. Okay, so from 100 onwards, everything will repeat. What is equivalence class of minus 1? Equivalence class of minus 1. You just try to find out which one satisfies, means minus 1 minus what is divisible by 100. Okay, that way you can identify what is the equivalence class of this. Okay. Minus 1 minus which number out of this? 99. Equivalence class of minus 1 will be same as equivalence class of 99. Okay. So we will do one theorem which actually says that class A is equal to class B if and only if A and B are related. Okay. B belongs to R. Okay. So this is a theorem. So whenever we know A and B are related, they will have the same equivalence class. Okay. So equivalence class is something like a group. Okay. Suppose you know your friend, or say WhatsApp group. Okay. If you are very known to each other, you can be inside the same WhatsApp group. Okay. Something like that. Okay. One is known to 101. So 101 they are in the same group. Okay. Then add another 100, 201 they are in the same group. Okay. So it is actually we are dividing the set into several classes. Okay. And there is some similarity between the members of the class. Okay. At the same group there is some similarity between them. What is that similarity? Similarity is this. They are related. Okay. So whenever two elements are related, they are placed in the same class. Ekta same jagah te place for us. Okay. So the set of integers, as you can see, the set of integers we can group it into equivalence classes. Okay. Plus minus 5, plus minus 10, plus minus 15. Okay, like all multiples of 5. Then here I can group it. So these are of the form 5n. I can group it like 5n plus 1, 5n plus 2. Okay. So I can write the set of integers as the set of 5n. Okay, union the set of 5n plus 1, union with set of 5n plus 2. Okay, like that. Up to 5n plus 4. Okay. So we can separate the set into different parts which are disjoint. Okay. So the same set can be broken up into pieces. Okay. Suppose Z is this set. Okay. Under equivalence classes, we break this Z into several parts. Okay. Suppose this is the equivalence class of 0. This is equivalence class of 1, equivalence class of 2, equivalence class of 3, equivalence class of 4. Okay. So this is actually called a partition of Z. Z you consider Z as a room. Okay, or a room. You want to partition that room. Okay, so we can partition it this way. There is nothing common between them. Okay, class A, class 4, class 1, class 4, they don't have anything common. Okay, so this concept is called the partition. Okay, breaking up a given set into several disjoint pieces. Okay, they should be disjoint. There should not be anything common between them. Okay. Right. So it's like a Venn diagram here. Okay. So this is also like a Venn diagram. In Venn diagram we do it with circles. Okay. So under this Venn diagram there is nothing common in between them. Okay. So something like this. So a singleton, this is 0, this is 1, this is 2. Okay. Something like this. This is 3, 0, 1, 2, 3, and this part is 4. Okay, like that. Something like this. So we partition the given set into several classes. Okay. So in the next lecture you will see that two different equivalence classes, either they will be the same or they will be disjoint. Okay, there is nothing common between them. Okay, if there is something common, they shall have to be equal. Okay. আর যদি equal না হয়, if they are not equal, then they have to be disjoint. Okay, there cannot be anything common. Whenever there is something common, the classes will be equal actually. Okay, so they are either disjoint or they are identical. Okay, these two are the things. So some 3 or 4 properties are there which are very important. We will do that. Okay. কেদা বুঝলাই নি একটু কঠিন হয়ে গেছে নি আজকে একটু কঠিন হইব যত দিন যাইব একটু কঠিন হইব Okay, I will give you some more problems. I will post in that Google Classroom. You can see. আরো কয়েকটা প্রবলেম দেবো, হ্যাঁ, তো try to solve. তখন বুঝতে পারবা।